I want to try to make number 1, and I thought I would graph this for you, and you can. So you need to have your notes out. I mean, it's only been like 7 months, 6 months. We do the same thing every day. We start off with our packet, so you shouldn't be shocked. I want you to start off here, but we're gonna make this. We're not gonna just like march through our examples. We're gonna try to hopefully do a good job of visualizing things and having this make sense. Bless you. Okay, so this says we're supposed to be finding some volume of this solid, blah, blah, blah. It kind of tells us a little bit about this. It says we're going to be revolving a region that is bounded by the graph of f of x equals cosine x and the x-axis on this interval. Going to be revolving that around the y-axis. So in order to do this, I need to understand, there's that smell of Play-Doh. I just caught a whiff of it. We got to understand what this region looks like. So graph of cosine of x looks something like that. Let me try one more time. From 0 to pi over 2, something like that. So it's pi over 2 comma, well, I'll just leave it as such. Anyways, can you see how that region on that interval is bounded by 0 to pi over 2, the x-axis, and then the graph of cosine of x. So what we're supposed to do with this, and this is what you saw in the video, and this is what we're going to work on right now with the Play-Doh, is we are supposed to take this region and we are supposed to revolve it around the y-axis. So, like so. So if you can maybe visualize what this looks like. Make it with Play-Doh. I want you to basically try to make this solid with Play-Doh. So this is like, I'm kind of just throwing this at you, but I want you to try. I want you to use the Play-Doh and try to form the solid where if you took that region and did revolve it around the y-axis, you'd end up with the solid shape around. Make sense? Oh, we'll see. We shall see. Is there any extra Play-Doh?
Does it have to connect?
What do you mean, does it have to connect?
If you revolve it around, like, does it meet the other?
So, you bring up actually a pretty good question. Do you see how the region is partially bordered by the y-axis?
No.
You see the orange region?
Yeah.
Do you see how the left boundary is the y-axis?
No.
So that's what I mean, like part of the region's boundary is the y-axis.
No, it doesn't.
So you said, does it connect? And I'm still not totally sure what you mean by does it connect. It probably is a good question, I'm just not understanding it. Can you think of a way to rephrase? Oh, I see. Are you asking if it's hollow?
No, I'm asking if it, like, if when it revolves around, does it, like, extend?
Whatever revolves around. I agree. It is sort of donut-y, I guess, except there's no, I don't think there's any hole.
Why is that hard?
Sure it is. There's like a lot of hole down there. Yeah. So I'm thinking, I don't know, you guys like the purple color? I'm thinking it should, I'm thinking the bottom of it should be really flat, right? The bottom of it should be completely flat, right? Because what is the boundary for the bottom of this? The x-axis, right? As you revolve that around, the bottom of it is the x-axis. But you see how the top is almost like, it's certainly not a circle, but it's like sort of almost like a hemisphere. Yeah. Except it's not totally spherical. It's kind of flattened off a little bit because it's cosine instead of a circular region. I like to do this sometimes too. What would this little part of a pen, what would that represent?
The y-axis.
Isn't that the y-axis?
The y-axis.
Isn't that the axis of revolution?
It's the y-axis.
Can you see it? The y-axis. There we go. I like it. Does that make sense? That would be the y-axis?
Yes.
Okay. So then the last thing I want to do, and I'll do this quite a few times, is I'm going to take some dental floss, and if you, that's slippery dental floss. If you ever want to do this too, I got more dental floss. What I can do is I can cut right through this thing, and hopefully see. I kind of erased my axis there. Let me do this. There we go. Interesting. How clean is that? Can you guys, can you see with that axis in there, can you see the region? Did you see how there's two regions? Like it's obviously been revolved around. Maybe like this one over here would be the one in the first quadrant. You see how that was revolved around the back side and then through the front side, eventually made this whole solid? Okay. So, of course, what we're going to be doing is we are going to be finding the volume of this. And let me remake it real quick. One way of forming some data was violent. Violent technique. Good. It's real good. So let's see here. Max, would you mind holding this? You know what? I like yours better. Can I cut yours?
Yeah.
Okay, so check this out. I'm going to cut it a little different direction. Could you like flip it 90 degrees? Okay, so hold it up real quick. Show everybody how you're holding it. He's holding it like vertically. He's like changed it so I can cut through it parallel to the x-axis. Does that make sense? So check this out. I'm going to cut through, and then I'm going to cut through. Hopefully it'll stay upright. It's not too terribly dry. Yes. Okay, so what I've done here is I've cut through, there we go. I cut through Max's shape. And as you can see, as I cut twice, you see the disc in there, like the circular like disc. I guess I kind of smashed one end of it just by the cutting of it. So you saw in the video, this is what we're going to be working on. It's called the disc method, right? It's like all these little pieces making this up could be sliced into little discs. That if you made them really skinny and added them up, you get the actual volume of the shape, right? So that's a little bit harder to see because the shape gets smashed. Maybe you can see how it's made up of a bunch of discs. Okay, cool. So, how do we do this? So I think there were a couple of principles in the video, and this is the part where we take the Play-Doh, and if we can't handle it, we put it back in the bucket, or if we can handle it, we just set it aside. We do a little bit of writing, and we'll go back to the Play-Doh in a few minutes. Okay? So please, Play-Doh. Put it somewhere else. Please don't make me do the first grade teacher thing where I have to say, guys, we're going to have to put the Play-Doh away now because you can't handle it.
That's how I feel right now.
And but I promise we'll get it back out in a few minutes and we'll play with it some more and we'll do it again tomorrow and the next day. Yes. Later on we'll get the graham crackers out and everybody will be happy. Okay. So let's see how much you guys remember from the video. Hopefully you remember a lot, but if you don't, we'll be fine. We'll survive. The best way to visualize this on paper would be to draw in a representative element. I often will call it a representative rectangle. So, First question. When I am trying to draw in one of these representative rectangles, what is the relationship between the representative rectangle and the axis of rotation?
It's
Well, yes, horizontal would end up giving us a bunch of y's, vertical would give us a bunch of x's, but and you're right,
It's
100%. What I'm getting at is, I've got this axis of rotation right there. Should I draw my representative rectangle like that,
no,
or should I draw it like that?
like that.
So what's the relationship between the axis of rotation, in this case that would be the y-axis, and the representative rectangle? What's the relationship we're looking for? Perpendicular. Perpendicular, right? So if you've got a vertical axis of rotation, like we do here, we draw in this horizontal, aka perpendicular to it, representative rectangle. And maybe you can see, based on having watched the video, you can see all these little representative rectangles that would be formed all throughout this shape, so on and so forth, rotating around, creating the solid that you all just made with Play-Doh. Sir?
What's the 3D shape of a rectangle? Like a square is a cube, a rectangle is a...
If a rectangle was rotated?
Like
Prism, rectangular prism.
Oh, really? Okay.
Yeah, I think it would be what it's called.
Thank you.
Yep. Okay, so guys, this really is the most important thing, right? So this sets the direction of everything. For instance, like if we were going to play a basketball game, and I said, okay, that's your hoop that you're trying to score on, and that's my team's hoop we're trying to score on. You might want to know that so that you can know that when you're on this end, you play defense, and when you're on that end, you're trying to score, right? And so what we just did set the direction for everything. If we don't get the whole, the relationship between the axis of rotation and the representative rectangle, if we don't get that right, everything else can be messed up. We're going to be trying to score on the other team's hoop. It's not going to go well, right? And so it's important for you guys to remember that the relationship between the axis of rotation and the representative rectangle is always perpendicular for what we're going to be doing. There's other ways to do this, so I don't want you to think this is the only way to do this. This is the way that we will focus on in our class. Okay, so here we go. If that's the case, here's what's said in my question.
How do you know which one is revolving?
You'll be told. It'll say, take this region defined by blah, 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 and rotate it around such and such. It'll definitely be told to you, otherwise there'd be no way of knowing.
Oh, so it's the around the
Yep, when it says around the y-axis.
in the sense that it's horizontal.
Y-axis is vertical.
Well, like since it's that, the rectangles are going to be horizontal.
Correct. Yep, they need to have a perpendicular relationship. And what you just said, as far as if this, then that, will be true. Will always be true for us. Okay, so what does that set in motion? Here's one thing, and this is really important. What is the thickness of that representative rectangle? Say again?
The change in y.
Change in y in calculus represented by dy. Okay. Okay, so we know we're going to be adding up a bunch of real skinny geometric shapes here. The only way to do that is with an integral, right? So I'm going to start this off with this. It's going to be integral. I don't know my limits yet. I don't know what goes on the inside yet, but I do know this. It's dy, right? I know that part, at least. I don't know anything else yet. So here's the next thing. And this is the main thing that I want you guys to take away from the whole Play-Doh thing. When you made your shape, my shape is still somewhat intact. When you made your shape, solid, did that solid have a hole through it? Like, could I look through it and see anybody? Say again? No, and this is the correct way to make it, the way we did it. It's the correct way to make it. So there is no hole in this, right? Also, kind of a follow-up question. Is there any way that I could take this shape and orient it in any direction? I don't really care whatever direction you think, and pour water into it, and it would actually hold water, like a bowl or a cup or something. I don't think so, right? I mean, this is a thoroughly solid shape. There's no hole, obviously. There's no hole I can look through. And I would say, and this is why, Addie, your initial question is quite important. If the shape looked like this, do you see how this could hold water? It doesn't have a hole in it. I still can't see through it, but it could actually hold water. It's got a big indentation or a big concavity in the middle of it. If our shape looked like this, or if our shape, looked like this, actually did have a hole in it, then we would take a bit of a different strategy than if the shape was just completely solid, no hole, couldn't hold water. Does that make sense? That's one of the big takeaways on the whole visualization of what this thing looks like. Okay. So anyways, once you've decided that, you said, all right, it's going to be a dy representative rectangle. That thing doesn't have a hole in it. There's no way it can hold water. This has set us up for what we call the disk method. And the reason why it's called the disk method is very simple. All the representative rectangles, when revolved, would form literally solid disks. Or maybe better said, little cylinders, right? And maybe you remember from the video, once you've arrived at a disk method, remember the disk method is for a solid that has no holes in it, and it couldn't hold water, just like totally solid. The way that we do this is simply pi integral r squared dy, which is the volume formula for a cylinder, or the volume formula for a little disk. That's all it is. So again, I think sometimes in calculus we see these formulas and methods, and we sort of think that it's magical, like, whoa, unbelievable. All it is, can you find the volume of a cylinder? That's really all it is. Okay, so let's do this. We need to handle the R. We need to handle a few things here. So let me ask you first, if I was going to accumulate all these disks to find the volume of the solid, do you think I would accumulate these disks from the left of the region all the way to the right edge, or would I accumulate them from bottom to top? It'd be a bottom to top type of a procedure, wouldn't it? Because I'd start off by finding the volume of that disk, and then I'd go to this one, and then I'd add that one, so on and so forth. Work my way up to the very top, and once I get to the top of the region, I'm done. Make sense? Okay. So then the limits of integration should reflect this, right? They should reflect the where do I start accumulating and where do I stop. So what do you guys think? Where would I start and where would I stop? 0 to 1. Yeah. Start down here at y equals 0. I'd stop up there at y equals 1. So my limits of integration would be 0 to 1. Does that make sense? Okay. And then again from the video, that letter R, literally, let's not overcomplicate this. It means radius. It just means radius. That's it. Sometimes it's helpful to define radius, like what it actually means. Isn't a radius the distance from the center of the disk out to the outer edge? Okay. So what I'm about to do might seem a little convoluted, but I think it'll have some value as well. Would you guys agree with me that the radius changes depending on where you are on the region? Like down at the bottom, the radius is pretty long. As you get closer to the top, the radius actually starts heading towards 0, doesn't it? Okay. So would you agree with me that this, from this blue dot to that blue dot, would represent one of the radii of our shape? So I'll connect that with a blue line. So that right there, that would be one of the radiuses, one of those distances from the center of the region, center of the shape, all the way to the outside. Okay? Can anybody define what that is? It's an x, isn't it? Yeah, it's some kind of an x distance. In fact, if we did start right there on the y-axis and measure out there to, wherever that is, to the right somewhere, isn't that the very definition of x? Like, remember when you first learned about the Cartesian coordinate system or the rectangular coordinate system? Didn't they say, hey, if you start at the origin and count right, we call that x. Or if you start at the origin and you count left, we call that x as well. Just negative numbers, right? So literally, from the y-axis out to the right, all that is an x. So, quite literally, if we want to be super literal about this, couldn't I erase that r and replace it with an x? It's simply the x-coordinate given whatever position we are in the shape. There's a problem with this, though. Everything has to be in terms of y, and that's why it's really important to set up the dy first, to realize, okay, the disk is dx thick or dy thick, whatever it is. We need to set that up first so we understand that everything has to be in terms of x, or everything has to be in terms of y. In this case, everything has to be in terms of y. So, anybody have any ideas as to how I could replace that x with something that is in terms of y instead of in terms of x? Yeah?
Can you do like the y-axis minus cosine or something?
The y-axis
This is 0.
minus cosine of what?
You could do like the inverse cosine.
Oh, okay, okay. Isn't she right that we need to do some kind of work with this? Let me rewrite that a little bit, and I think we'll come back around to what she was saying. Isn't this really y equals cosine x? F of x, same thing as the output, right? It's the y. Okay, so then what could I do with that so that it's x in terms of y instead of y in terms of x? It's that inverse cosine, right? The arc cosine, yeah. So I just do the inverse cosine of both sides, so it'd be inverse cosine of y is the exact same thing as x. So you see now, couldn't I just replace that x with the inverse cosine of y, which is what I wanted in the first place? So it'd be the inverse cosine of y, quantity squared, dy for my integrand. This is not an integrand that you'll be able to handle without the calculator. So please take a minute with your calculator. Use Math 9. See what the answer approximately comes out to be.
What about like the fact that it's not personal?
Okay.
2654.
Say just the first three decimals.
1.142.
1.142.
3.586.
3.586.
That's what I thought.
3.5. Luke is saying yes on the 3.586.
I got
Okay, so this, I think, the errors, hey, listen, the errors, whatever they might be, are welcome. So let me just ask, Jake, I'm thinking you probably forgot the pi because you're about 3 times too small. Was that it? Okay. So 2 common things that get forgotten. Almost no one ever forgets, I got to deal with the radius, right? And they often will get that correct. People will forget the squared, and they'll forget the pi. So Jake, maybe, I don't know if others are doing this, but for you, for everybody, for my own self, just so I don't, because I'm just as susceptible to forgetting those kinds of things as you guys are. If I put this in my calculator, you know what I put? I go pi math 9. Pi math 9. And then I fill in all the details on the math 9. Because I know myself well enough, if I just do math 9 and I get all that stuff put in there and I hit enter and I get an answer, and be like, sweet, done. Forgot to go times pi, right? So if you just go pi math 9, then you're setting yourself up for success. So consider. Hey, I thought I'd show you another little visual here, kind of like you saw in the video. Check this out. This is the same region, right? Same region. Can you visualize in your mind, what if I took this region and instead of revolving it around the y-axis, what if I revolved it around the x-axis? Can you sort of picture what that would look like, just mentally?
It'd be weird,
Revolve around the x, not the y.
oh, it's the same thing.
Picture it in your mind. Try to ask yourself if that resulting solid would have a hole or the ability to hold water.
No.
So let's revolve. Let's see what this looks like. So if I take this, maybe change the perspective a little bit, and we start to revolve it, maybe just part of the way. Can you see the region still? And we start to see this shape, this solid taking shape. And I'm gonna fill all the way. There we go. I want it all the way solid. If I continue to rotate all the way around, I think you can see pretty easily that this, there you go. Oh, it's kind of freezing on me a little bit here. Come on, GeoGebra, you can do it. That's actually a pretty good angle, I guess. Huh, maybe it'll move in a second. So can you see? So here's the important takeaway. Can you see how that region does not have a hole and could not hold water? Make sense? So what method would I use if I was going to try to find the volume of that solid? The disk method, yes. Disk method. Later on we'll find a new method if there is a hole, or it could hold water.
Wait, the
Wouldn't
ones,
it
what's
be the
the...
same volume?
This one, different volume. You could find it, prove it to yourself. You want to do that?
It's the same.
Okay, hey, I'll tell you what. Let's do it. Let's prove it to ourselves, one way or the other.
Why would it be different?
Could you do it?
It's a different shape. Okay, so let's do this real quick. Go ahead.
Couldn't an example something to hold water be like the one we just did, and then like the area in between that one and like a cosine graph with like a smaller period?
Yeah, definitely. There's a lot of ways we could make it, but that would be
Some other ways.
basically any two different functions. Yeah, parabolas, cubics, natural logs, all these different graphs we could do.
Cool.
Yep, we'll do quite a few of them for sure. Hey, Addie, let's prove it. Let's prove one way or the other. So if I go back to that same region, here's what I would do. I would say, there's my cosine graph. That's 1, that's pi over 2. Here's my region. So as you mentioned, what if we rotate around the x-axis like we saw in the little animation? Would this be a different volume or the same volume? Let's reinforce this. I think you guys know this. What's the relationship between the representative rectangle and the axis of rotation? No. What's the relationship between the representative rectangle, the little thing I could draw in there, and the axis of rotation? Perpendicular. It's very important that we start there. If we don't get that set, that would be like starting a basketball game and the referee not telling you which hoop you're trying to score on. You might score on the wrong hoop. You just don't know. We got to start there. Why is that so important? That establishes the thickness of the representative element. What would be the thickness here? No. Thickness is dx. Thickness is dx. In other words, like the thickness is measured as a little itty-bitty change on the x-axis. Does that make sense? Okay. So what that means is this. My volume is going to be pi integral dx. I haven't figured out anything else on the inside there, but I do know that. The next thing I would decide is this. Is the resulting solid going to have a hole in the middle? Could it hold water? Or is it just totally solid? Totally solid, isn't it? So we would use the disk method. So that is pi integral of r squared. Right? Maybe the next thing I would do is I would set up my limits of integration based on the way that representative rectangle is drawn in there. And I totally recommend you draw one in. It'll cost you like 1.4 seconds of your life, but it's probably time well spent. Well, hang on. In what kind of pattern am I going to accumulate these? Is it going to be bottom to top, kind of like the last time, or this time it's going to be more left to right? Yeah, aren't these representative rectangles in that pattern, going from left to right? So if I am going from left to right, where would I start accumulating? For which x value? 0. And where would I stop? Pi over 2. So there's already a difference there, right? 0 to pi over 2 versus 0 to 1, like we did when we were rotating around the y-axis. And then lastly, the radius. Remember, the radius is simply distance from center of the solid out there to the outer edge. Clearly, I think it's going to be the distance between these bright blue points again. Not very bright. Let's try this. The distance there would represent the radius. So if I drew that in, that's my radius. If you wanted to be super literal and very elementary about this, how would you describe that? It's y, isn't it? Yeah, isn't the distance from the x-axis up? defined as y. So if I wanted to, I could replace the r with a y. Why is that so terrible? Yeah, everything's got to be in terms of x because it's a dx thick representative element. What is the one thing I could put in place of the y that's in terms of x? Yeah, y equals cosine of x. So I could replace y with that. So it would be cosine of x, quantity squared dx for my integrand. You plug this into Math 9, and we got, what, 3.586 or something like that for that other one? I think I'd be willing to bet that this will be something different.
2.467.
Guys, anybody else do that? 2.467? Okay, yeah. So, clearly a little bit smaller. So it's different. Say again?
There wouldn't be units
Unless I gave you units. So let me ask you a follow-up question to this. So Addie said, and I think her question is good, and I think it's going to lead us somewhere. She said, wait a minute, shouldn't the volume be the same if you take that region and rotate it around? I think we just proved that the answer is no. However, can anyone think of the case in which the volume would be the same? Yeah. What if that region was defined by a quarter circle? Wouldn't this and this be the same? And wouldn't the radius be a constant 1, or whatever the radius is supposed to be, all the way around there? That would be the case where it really wouldn't matter whether it was x-axis or y-axis rotation. You'd still get the same answer, circular. Cool. Any follow-up questions? Anything at all? Okay, let's see what's next. This will be our last one. Number 2 is, there we go. Okay. So guys, take a minute, use your calculator if you need to. Figure out what this region looks like. Use your Play-Doh. Please try to make the solid that would result from doing that. Okay? Ready to go. Oh, let's see here. Let me sketch the region out real quick. You got the y-axis, you got the x-axis, and then hopefully you arrived at a parabola for this. Here goes my first attempt of the day at drawing a parabola. Ooh, that side was pretty good. That side was not. I know, I feel the pressure, Tim. Oh, boy. Yeah, that was terrible. Okay, here we go. Nope. Ah.
This is where you put it down on the table to make sure.
Oh. You could top it.
That's good.
My finger was getting stuck. I'm going to call that good. I was like trying to slide my finger, and I was like hitting the side of the iPad and getting my finger stuck. I was getting real nervous at the end. Okay, so please pardon the squigglies there at the end. Would you guys agree that this red highlighted region is my region that I'm going to be rotating? Right, the whole thing. Okay, so the axis of rotation, I am told, is the x-axis. So I usually draw in that little rotation symbol to say that's my rotational axis. We tried to visualize it with the Play-Doh. There it is. You all saw it. And remember, what's the big takeaway from the visualization process? Yes. Does the solid have a hole, or could it hold water? And if the answer is no, it's just totally solid, water would just flow off of it. There's no hole in it. We've got to use which method? Disk method. Okay. So disk method because it is just totally solid. All right, what's the relationship between the axis of rotation and the representative element? Perpendicular. There we go. So I'll throw one of them in right here. How thick is that? dx. So that right there is the referee saying, you shoot on that basket and you shoot on that basket. We know the direction of this now. We know it's going to be volume equals pi integral, we don't know yet, dx. Make sense? And because it is solid, No holes, guys. Again, this is the period in time when the Play-Doh needs to just do somewhat of a disappearing act. We'll play with it again tomorrow, don't worry. It's at this stage we got to realize, because it's the disk method, it's going to be pi integral r squared dx. And we start filling things in. So I like to do the limits next. So aren't I going to start accumulating over here on the left and stop over there on the right? I'm going to be accumulating across this region from, bless you, left to right. So where would I start? For which x value would I start the accumulation? It's this x value right here, right? And I think you said negative root 2. Anybody want to explain where you came up with that negative root 2? Yeah, set y equal to 0, because that's what is going to happen when the graph is hitting the x-axis. Y will be 0. Okay, so is there symmetry? Is this over here positive root 2? It is, yeah. So there is some degree of symmetry here. So how about that? And then finally, the r. The r is the distance from the axis of rotation to the outer edge. So that would be from blue dot to blue dot. You can see that's going to change depending on where you are in the region. So how would you guys describe this blue length? It's literally y. Yeah, if you want to be super basic about it, it's a y. What's wrong with leaving it like that? It's got to be an x. What is y equal to? From right up here, y equals 2 minus x squared. So I could replace that with 2 minus x squared squared. Does that make sense? So this can definitely be done with Math 9. This can actually be done relatively easily without Math 9 if you FOILed out that binomial and then did an antiderivative, so on and so forth. But I do want to point one other thing out before we go. I'll let you Math 9 this. I'll let you antiderivative this, whichever one you want. I don't really care at this stage. But I thought I'd show you one alternative approach to this. And Addie, I thought you were going for this, but you didn't quite. What if I did this? What would be, other than changing the 0 back to what it was before, what would be one minor change I could make so that this green integral has the same value as the black integral? Times 2. Why? Oh, the symmetry. Did you notice? I'm sure you did, that this right half is exactly the same size and shape as the left half. So why not start at 0, just go out there to root 2, and then double the result? What would be wrong with that? Nothing. That would be perfectly good. And why would you do that? What would be kind of a side benefit?
Quicker?
Why? It would be, I agree, I think it would be quicker, but why?
I mean, if you're not using a calculator, doing
If you're not using a calculator, agreed? Keep going.
the antiderivative of negative root 2 and foiling that all out and doing it actually would take a lot more time.
Why? Because this number is,
0, just simple 0.
and with a polynomial, 2 times 0, 0 squared, 0 cubed, they're all just 0, aren't they? And so I agree, this could be a time saver because you would know, because it's all just polynomial stuff, the result will just be 0 when you plug in a 0. Take whatever results you get and just double it. Do you see why that'd be easier? Far from required. You can certainly do it the way that we had in the black integral up there, the black expression. The green maybe would be slightly better. Up to you. Did you guys get an answer for this one? 18 point what? 956. You guys agree with that? Okay, awesome. So, you guys are now into volume. It's not that bad, is it? Pi r squared. And guess what the washer method is, which is what comes next?
Like washers,
Pi r squared minus pi different r squared. That's how you get the whole subtracted out. That's really all it is. So I don't want you to overcomplicate this or anything. Hopefully you've had fun with Play-Doh. We will continue. The Play-Doh will be here all week long. So have a great day. See you guys.